Hello, welcome to the modeling segment of the NIH mHealth online course. My name is Misha Pavel. I'm at Northeastern University in College of Computer and Information Science and also in Bouvet College of Health Sciences. I'm going to talk to you about a couple of issues that relate to modeling. And here is our roadmap, just to give you an overview of the two approaches that we are going to address. Modeling, mathematical modeling, is a way to describe systems and objects that allow us to map them into formal frameworks that allow us to manipulate them in a way that's much easier than using empirical evidence only. First of all, I would like to convince you that actually every one of you already is a modeler. In particular, whenever you analyze any data, you have an implicit model. For example, have you ever computed averages, like this one? If you have, then you had to ask yourself, why did you add numbers? Why did you not multiply them, square, logs, etc.? Well, that's because you had an implicit model of the underlying process. The model was random variables taken from the same distribution, and you are attempting to compute the mean or the central location of that distribution. If you make these models explicit, you will be much better positioned to avoid issues like biases, etc. So before we go on, we have to ask ourselves, what is a measurement? Well, we understand measurement is converting physical or abstract objects into quantitative sets, like numbers, while preserving relationships and preserving operations. So usually you are interested in a phenomenon and would like to convert it into numbers. The numbers then represent aspects of the objects that you can use to operate on, make predictions, make assessment, make inferences. That process is called measurement. But every process like that requires a model. And that model is then inverted to allow us to make inferences. To make it more clear, let me go through an example of measuring mass. Well, if you want to measure my mass or mass of anybody, you can't measure it directly. In fact, the only way we can measure mass is by using a model. And that model converts mass into weight, and weight is force, represented by force. So that's the first part of a model. The second part is then, how do you measure force? Also requires another model. For example, a balance. In case of balance, you're comparing two forces, on the left, on the right. If they're equal, then the mass on the left is equal to the mass on the right. That is a way we measure objects by comparing them to each other. There is another way, and there are many other ways, but another example is a lever balance. For example, the medical scale or the scale on the left are such levers. In levers, you have two objects, one on the left side, one on the other side, and the distance between them is implicated in making the measurement, such that the momentum is preserved, and therefore the mass on the left is equal to proportional to the mass on the right, divided by multiplied by a ratio of the two distances. Again, this is a model, and without those two models, we could not make measurements of mass. When you measure anything, usually almost always, you don't find the same measurements even when you measure it twice or 3 times the same thing. Therefore, there are little errors. In order to be able to handle that, we need to actually account for those errors. Repeated measurements must be modeled in order to be able to make inferences about what the real weight is. So what do? We build this model. In this model, simplest model, is the observed mass, the one with the hat on the left, is equal to the mass of the object plus some error. If the measurement is unbiased, then the error is distributed perhaps normally, but with 0 mean, as indicated here. If you know the parameter sigma, then it is possible to actually estimate the error that you make at each measurement, for example, within the sigma to sigma. Now you can ask yourself, are there other models of errors? Of course. If the distributions are skewed, you may want to use log normal distribution, and in which case you may want to compute geometric mean. Now, if we take this example literally, we cannot measure phenomenon directly, but rather go through 2 model stages: the effect of noise and force, and then the sensor effect. Those transformations are then used to make the inference. Now, here is an example of a more complicated modeling scheme. If you, for example, want to use mobile health technology embedded in an iPhone or Android to measure smoking behavior. Now, again, you can't measure it directly, but this is work by Santosh Kumar and his colleagues, where they take a number of measurements, including physiological measurements, pulmonary movement, and head movement. So if you smoke, your head movements are a certain way, and that measurement can be then converted to or sent to a recognition scheme and inverted and make inference about smoking. Again, you're required to take the sensors, combine them, and then model that combination and make inference from that. As an exercise, you can think about when we measure body temperature, what do we really want to know? I doubt that you really want to know how hot my body is, but you want to know something that the temperature is telling you about my physiology or metabolism and so on. Similarly with blood pressure, oxygenation, heart rate, and glucose concentrations. In each case, you can build models that relate the phenomenon that you're interested in, like, for example, the energy expenditure due to, as reflected in heart rate, and convert it to the quantity that you want to really measure. So much for measurement. There's much more, of course, to be said about measurement, but for the purpose of this course, we are going to stop here. So now we are going to talk about actually modeling phenomenon that you are interested in. When you use mobile health or any other measurements and observations, you want to make inferences. And those inferences are based on your knowledge about how the measurement relates to the phenomena that you want to measure. Now, there are whole sorts of models. And I ordered these models here in order of the amounts of data on the amounts of knowledge that you put in. So on top are models that contain very little prior knowledge and almost all data-driven. On the bottom, the systems are based, or the models are based on principles that are derived outside of the data. So in mathematics, we call it weaker models that are data-driven because they incorporate less knowledge, and stronger models for those models that incorporate large amounts of knowledge. The models that do not have much knowledge, prior knowledge, are generally explanatory, and whereas the models that incorporate a lot of knowledge can be very strongly predictive and generalize beyond the data set on which they were derived. In the sequel of this presentation, I'm going to focus a lot on the statistical data-driven models, but at the same time, we will also spend some time on the predictive models that include principled knowledge. Just to familiarize you with the notations that we often use in these representations, using matrices and vectors. So we typically have three types of quantities that are organized in arrays and square matrices. On the left, we have the trial number, assuming that there are more than one trials, as usually happens when you following a person through a sequence of events, or it could be trials with number of different subjects, etc. Then you have the dependent variable, y in this case, and that's a vector also. In this case, just a single number at each location. And that represents the output or dependent variable that corresponds to each of the trials as indicated on the left. And then we have a bunch of independent variables, in this case 2, that are summarized in a matrix that has 2 columns and the number of rows equal to the number of events. So in case of regression, for example, as you see on the equation below, the model that we construct consists of a number of constants that are represented by a's, a0 through a2. The a0 is a bias, is an intercept. a1 and a2 are multipliers of the independent variable, and e epsilon represents an error, which again, in general, will have 0 mean, but just to be general, I represented it by mu. Now, this is the model. The model means that we believe that each real output number or dependent variable is a sum of those independent variables multiplied by proper constants. But when we actually look at the data, we don't know those constants exactly, and we have to estimate. And the equation on bottom differentiates from the top equation, or the equation in the middle, with the little hats. Those indicate that we have estimates. So for each values x1 and x2, we have an estimate of value y. And what we typically do in regression is try to figure out the values of a0, a1, and a2 that would minimize the difference between the observed variables y and the estimated variable y hat. This is just an extension of the previous slides, and what we are looking at is, in addition to the data and independent variables, also the coefficients a0 through an can be put into a vector. And if we do that, then the regression model, the equation right below the matrices, can be written very simply as indicated on the right. So as you can see, this is a shorthand notation using matrices. The A prime corresponds to transpose, and transpose is just an operation that takes a vector and rotates it by 90 degrees. So if it were a column vector, it becomes a row vector. It's, again, simple notation so that we can use matrix multiplication. And you can look up any very simple, very low-level algebra books, linear algebra books, to see how this is done. An important concept for regression is correlation. A correlation takes two variables and computes the product relative to their variances. And we show this correlation matrix for this particular case of two independent variables on the bottom of this slide. Correlations are very important, but sometimes when we have data that we don't know much about, we have to be very careful about how we interpret them. This is a graphical representation of a regression that was shown on the previous slide, where each variable, independent variable, is shown in the bottom part of the graph and the dependent variable on the top. Each link represents correlation that is then proportional to the coefficient. And this is just to show you a graphical representation of a regression. Correlation is then used to compute these coefficients or estimate those coefficients. This actual data, actual denomination of the variables like cost of parking and perceived effectiveness was taken from a project that involved cardiac rehabilitation, and these data were used to estimate the number of visits to the center by different subjects as a function of their perception of the effectiveness, cost of parking, distance from the center, etc. It's a virtual problem just to help you indicate by example of what we do. Ideally, we would collect lots of data on lots of patients and then compute these correlations. Now, if we have lots of data, we then talk about big data. Now, big data does not really necessarily mean very large amounts, but it means that the data are complex and not well understood and need to be analyzed by new techniques. But in this case, we can still use a regression. But I would like to caution you about using big data, and we'll talk a little bit about that for the next 2 or 3 minutes. Now, the reason why we bringing up big data is that mobile health enables us to collect enormous amounts of data as we can continuously sample the location, accelerometry, environmental conditions, and even physiological measurements for people who wear or carry their mobile phones. The general notion is, and you come across this a lot these days, is that for big data we don't need hypotheses, we don't need to build models, because these can be generated from the data. And we also hear that there is no need for sampling. Well, first of all, about sampling. Almost always you sample. Even if you have all data, typically you don't have the entire population. There are very few examples where you actually have the entire population. And it's very important to understand that if a sample is biased, it doesn't matter how big it is. It's still going to lead to biased results. So be very careful about using n equals all and assuming that it's unbiased. Now, to convince you about the importance of knowledge, let me bring up these few examples. If you just look at correlation, you may find, for example, that purchasing diapers is very highly correlated with drinking beer. And so if you take this seriously, you perhaps would prevent buying diapers in order to reduce drinking. Can you think of a reason why that would be? Why that correlation would be there? Well, it turns out that on Fridays, people buy a lot of diapers and a lot of beer. And so they are correlated by the time, by the conjunction of time. Same thing happens when in the old days when we had polio, when you correlate the number of soft drinks with polio incidence. The reason for that is that polio usually is contracted in the summer, and people drink more soft drinks in the summer. And finally, same reason is correlation between ice cream eating and drowning. In the summer, people eat more ice cream, but also there is increased proportion of drowning. So clearly, you wouldn't want to derive principles from these kind of correlations. How do we handle it? Well, you have to think about what could be causing this correlation. And typically, in these three examples that I showed you, it's a time or season. Sometimes it's location that enables or that forces correlation between two variables that normally are not connected at all, but rather occur at the same time. So this is an example, a graphical example of how polio is correlated with the time of season in a year, and so are soft drinks. Now, to avoid this kind of problem, we approach modeling in several ways. Factor analysis is one of those approaches. In factor analysis, we try to find a smallest number of linear elements that would characterize the whole data set. And we don't necessarily know what those variables are, in this case y1 and y2, but by looking at the data, we may conclude and give them interpretation. This model is factor analytic model, and it's represented by this equation. In hierarchical representation, we might do a similar procedure, but set out to correlate a priori subset of the variables as shown here, and then the output variable is a function of the intermediate latent variables. This is particularly a general approach that is called structural equation model, where we a priori decide that there are latent variables, and we even give them names, that characterize the dependencies, linear dependencies in this case, among variables, like input variables or other latent variables. But in addition to this hierarchical representation, as shown on this animation, you can also have a feedback loop. This is very important. The feedback loop now, in this case, in this simple example, the number of visits to the cardiac center influences your perceived effectiveness of the patient and their motivation. And so there is a loop. Structural equation models are only valid for a steady state. So once the loop has been run through several times, it is assumed that this system goes to steady state, and we can then compute the correlations. As such, structural equation models are limited to static snapshots of the situation. You have to keep that in mind when you're trying to use structural equation models, which are reasonably popular these days, to model situations which are dynamic, where motivation, number of visits, and perceived effectiveness, for example, in this case, change over time. Now, you might have been concerned with the fact that I was talking mostly about linear system. Of course, you can generalize this linear system in a variety of ways to include nonlinearities. And this is one of those cases. Generalized linear model is well known, and this is why I presented here. Again, although it's data-driven, it does incorporate much more knowledge. In particular, the function f represents a transformation between the linear combination and the output. And a good example of that is a logistic regression. And here, representing in this example the dose response curve. If you measure dose response, that is, you measure responses to a dose at different value of dose, you get these values. And if you were to model them exactly, you would have come up with this curve, and you would need a lot of parameters to characterize response at each point. However, if you know that the underlying model is a logistic function like this, then you summarize all the points with just two variables, as if you were dealing with linear regression, but the output function is actually nonlinear and represents the probability of a response as a function of the dose. So this improves greatly the efficiency, statistical efficiency of the estimates, and reduces the number of points that we have to take for a given error tolerance. Finally, I just want to mention that you can generalize these models to hierarchical Bayesian models, as shown here, where the probabilities are considered at each location of the, at each node, rather than actual values. So this is much more general model, and that deals with much more than just the expected value, but represents the entire distribution. And you should, if you are interested in this approach, there are a number of books on how to do that. Now, if you remember the order of my different models, I started with completely data-driven, went through an intermediate stage, which were functional equations, and then principled approaches. Now, functional equations do not represent detailed principled knowledge, but they provide some principles that are incorporated. And once we have those, it is much easier to come up with models that constrain the data and enable us to make better inferences with fewer data points. One example of these functional equations is scale invariance. If the same, for example, if you have a two-dimensional object with dimensions x and y, and the object is the same, whether it's large or small, in terms of the interpretation of the object, like when you're looking at something at a distance, and then you come closer, you want to make sure that this object doesn't change its properties, except size. Then there is this invariance, where if you multiply both sides, or all dimensions, by some factor lambda, the object doesn't change. First order homogeneity, on the other hand, when you multiply an object by a number, say the dimension by a number, the output is multiplied by a number. For example, in case of coefficient of variation, you want the variance, or the standard deviation, be proportional to the value of the variable. And that's represented by the first order homogeneity. A more complex invariance is one that's used to characterize a mass-body index that has a more complicated relationship. And I'm going to explain that on the next slide. In mass-body index, as you know, you're essentially assuming that the quality of life or quality of health state is actually a function of the weight divided by the height square, which means that some quality Q of a person who has height h and weight w is the same as the quality of life given by the ratio. So instead of two variables, you have one. And what does that mean, actually, when you think about it in physical terms, is that h, the height, and width, and depth are the three variables that describe the object, like us. And the fact that the invariants exist with respect to w over h squared means that one of the dimensions is not relevant. And in fact, there are data suggesting that just the perimeter of the trunk would give you good enough representation of the value of the height represented in this equation. And that is actually derived from first principles. These are data just to show you that, that maybe there are some curvatures that need to be analyzed, but generally there is an increasing relationship between BMI and fat. Now, another invariance is that the difference in weights from day to day and variability of weights is proportional to the weight itself. This is very important because, especially for example, for congestive heart failure patients, we give them typically the threshold that if the weight changes by 2 pounds in a couple of days or something of that sort, they should call the nurse or start taking diuretics, etc. But if a patient weighs 250 pounds, 2-pound variation is nothing. And this kind of threshold should be adjusted with respect to the weight. This is just one example of how to use models to actually generate therapeutic interventions. On this slide, it shows you that although there is a relationship, linear relationship between average weight and the RMS, that is the deviations, it's not perfect, and we still have to look at individuals. This is very important to understand, that we need to look at individuals in order to make therapeutic interventions optimally. Now back to mobile health, and I'm showing here the kind of general principle where we, on the left, we have perhaps even a young person being monitored with a mobile phone using variety of sensors, both physiological and physical. The data are communicated to back office. They are stored in a cloud. And then intervention can be also mediated by the phone. And there are a number of many studies along these lines. Now, if we use accelerometer to measure activity, we are making a number of assumptions. And here is an example to show you what the most primitive assumptions we are making. If we represent the runner as a mass with friction and spring, the work that's done is then integral of the force over time, over space, or the x dimension, and that would tell us that we can take the acceleration and compute the power in the acceleration and use that to estimate the force, and then as well as the distance over which the force is applied, and use that to estimate the activity energy expenditure. But is this model good enough, you can ask? Well, it depends. In a controlled condition, it would be. If you actually have a subject walking or running, it probably will do well. But in absence of that context information, there could be all kinds of things going on, whereas the subject may be riding a bus or a car, or over cobble streets, or it's on a horse, and you can let your imagination go. So it's very important to know what the limitations are when we make these kind of assumptions about relating what's measurable, in this case the acceleration, to what we want to know, in this case energy expenditure. We already talked about the smoking example, where we take measurements of physiological, pulmonary, and arm movements, physical movements, to infer that somebody is smoking, and that's very useful. But we have to be also very careful that we look at all these different characteristics, because by itself, hand movements may not be a good enough representation, because as I'm sitting here and gesturing with my hands, it might seem to some that I'm smoking if they only look at the accelerometer. Now, these data were collected not from mobile, but from stationary sensors in a home of an elder person in Oregon. In Oregon, we have an organization called Orcatech, that's part of Oregon Health and Science University, where we developed a monitoring mechanism for monitoring elders in their home. These, each dot represents firing of one sensor telling us that the person is moving in a given room. The green corresponds to bedroom, the red bathroom, and so on. Each day is represented by one circle. In the middle, it's beginning. And as we go out, we follow the subject for a year. So this is a summary of an entire year of that subject's life. I'm showing this to demonstrate how important is visualization when we're looking at data that are collected in the wild. This person gets up in the morning, which is past the horizontal axis to the right, and then prepares breakfast, the first purple segment, then prepares lunch, then dinner. This person very seldom uses the front door, which means that they are mostly at home. And so it may be that we should look into their social environment and see if we can maybe improve it. Another interesting feature of this graph is that the first half a year, as shown in the right quadrant near the center, this person slept well. But the second half of the year, shown by the green dots in the bedroom, there was motion in the bedroom. This person slept less well. We don't know exactly why, but now we know that, and we can go back and try to investigate what happened, what changed, and how can we intervene to make their life better. Now, this kind of analysis is subjective, looking at the data and visualization. To make it more precise, we actually built a model that's, in this case, Markov model, which is not necessarily the best. In fact, Markov model allows us to try to estimate states, for example, which room the person is, and then look at the transitions, and then monitor these transitions, see if they change over time, and infer from them activities. So this is the type of modeling. Now, I wanted to make a point here that actually, in this case, we cannot use Markov model because the amount of time that a person is in a given room it depends on the room and may not be consistent with Markov model. I don't have time to go through the details, but just to let you know that this may be a good technique to analyze data that correspond to activities and actions of subjects that need to be understood to know how well they're doing. The final part of the course I'd like to spend on the models of the optimization of intervention. The general idea is that if you want to intervene, you're really trying to control the state of the person to some extent. It is as if we were driving a ship and wanted to come to a port or leave a port, especially if the ship is large. You have to really understand the dynamics of the ship in order to be able to steer it. And good skippers do that naturally, intuitively. And nowadays we have actually mechanisms that enable autopilots to do optimized control of the ship. In a similar way, if you want to help people change their behavior or help them do something that they don't do, it is important to know what effects your intervention will have and be able to predict those interventions. For that, we need to have a state estimation, a model that enables us to estimate the state in which a patient is. For example, are they ready to change? What would be the best input for that change? We can then, having this information, we can then use optimal control design, or sometimes very simple design, that would enable us to modify the state of the patient in a direction that they want to modify them. And I cannot emphasize enough how important it is to have a quantitative predictive model in this situation. And we have very few of those. They are emerging as we speak. But the development of these models will enable us to be much more effective in delivering the most optimal interventions. And I'd like to quote Levin's notion that there is nothing more practical than a good theory. And believe me, found that many times in my life. Here is an example of weight control situation. There are two models, actually, that need to be incorporated here. On the left bottom box is behavior model. Behavior model takes inputs such as social norm, environment, economics, you name it. I just showed three here. It then takes into account the current state of the patient or individual. And the output of that model is actual behavior. In this case, we consider two aspects of the behavior: the diet, the choices that the patient makes for diet, and the physical activity, exercising or not. Once we understand and can predict and observe the diet and physical activity, we can then input it into a model that describes the energy balance of the person, including the metabolic rates and all the characteristics that are associated with it. The output is then the weight of the patient and perhaps some other variables like lean mass or amount of percentage of fat as we measure it with scales that are available these days. Now, let's look at what we would like to do is use the measurements that the subject has together with the behavioral model and develop optimal intervention. In order to do that, we have to have these three components, right? We have to have the behavioral model, the energy model, and then developing the intervention. The model of energy expenditure, given activity we already discussed, and let's assume that for the purpose of this work of intervention, and for the purpose of this intervention, this model is sufficient. In addition, we need to incorporate energy balance model. And this is one example, a small subset of modeling that came from Kevin Hall and his colleagues, that takes the energy in the first equation, that takes the energy that's inputted on EI, subtracts the energy expended, and computes the energy balance. Energy balance is then used to modify the body weight. And body mass is the sum of fat mass, lean mass, and water. And these other equations just describe the kind of adaptation that happens as a function of the input energy that's remaining after expedited energy has been subtracted. So this is just to give you a flavor of how to build it. This is not a complete model. Again, you can look at the papers by Hall and his colleagues. Now, we need to also model behavior change. Now, there are a number of models that are often specified in fairly subjective and vague terms, but can be converted into a very quantitative form. This is one example of taking trans-theoretical framework that consists, that's based on the assumption, first proposed by Prochaska, that there are 5 stages, and the patient or individual moves from one stage to another as they progress through their behavior change. In pre-competitive stage, they actually not aware that they need to make any changes in their behavior, but as time goes on, as they move to other stages, to contemplative preparation and so on, they are more ready to make the change. What is important here is that we cannot observe this directly, but we can observe the kind of responses that subjects make and make inferences which stage they are in. And this is what the good coaches do when they do motivational interviewing. There are many other models, and I don't want to give you impression that this is a particularly good model, but it's one of the models that people have been using in conjunction with motivational interviewing to make the inferences and then to decide on intervention. Once you have this model, you can then plug all these 3 models into this framework and develop intervention that's optimal. This is my weight, and I just wanted to show you the variability of the weight, because we often think that we shouldn't weigh ourselves too often. Well, you cannot weigh yourself often enough. Because of the variability, you actually want to know what the variability is, so that when the weight is larger or smaller than expected, you can assume that some of it is due to variability. And understanding this variability is still a subject of current research. The reason I want to show you this graph is that in real data, and something that I haven't spoken about, there's often missing data. Missing data could be a real problem if the data are not missing at random. And unfortunately, in case of weight, for example, that often is the case. Because, for instance, we go on vacation, and on vacation, we often eat more. On the other hand, we might exercise more. So we can see that little the red line represents the median estimate of what's happening when we had in conjunction with the data. And you can see that there was a decline in weight for when I was gone for a couple of weeks. The other hand, on the right side, I am probably nervous and anxious and start eating very much. And I realized that I was starting to gain weight, and I developed intervention where I reduced my intake. And unfortunately, it takes a little bit time before that curve turns over. Understanding the dynamics is important in developing interventions, reward system, and appropriate feedback to people to be most optimal. So in summary, I would like to draw your attention to the benefits of computational models, some of which we have already addressed during our presentation, but some of which we didn't. We didn't much talk about the fact that these models also explain. If you have a computational model that's based on principles, the computational model can explain what's going on, and because of that, develop new questions that force us to do research and learn more about the underlying principles. Of course, we discuss that inference can be made much more efficiently from observable behaviors or from observable data if we have such model. We can characterize uncertainties and variability if we understand which aspects of the measurements that we observe are due to variability and randomness and which are due to dynamics of the system that underlies, like the case of the weight. We can guide data collection, and in fact, I insist always on my graduate students to have a model before they even design their experiment. And the model will be changed. But if you do not have a model, you're likely to make wrong assumptions and reduce the effectiveness of your experiment. We already discussed optimization of interventions, and of course there are political implications of understanding why something happens so that we can develop policy in public health or in individual therapy that would optimize the behavior. Where can you get help? Well, this is a multidisciplinary problem. In fact, I like to call it transdisciplinary, where we need to integrate many disciplines in order to make this work. And this is one of the reasons why the field hasn't gotten as far as it could have. The measurement and experimental design, we need behavioral scientists, but also engineers who will enable us to build systems, devices, and sensors that would be most appropriate to measure what we need to measure. For the data-driven and black box, we need statisticians. But for the more principled models, we need scientists, biologists, physiologists, system scientists that will tell us about the principles that can be incorporated. And finally, for intervention optimization, it is very important to include behavioral scientists, clinicians, and health professionals. And what we often do is ask coaches, what would you do in this situation? And use their output to infer the principles that they are using to make their decision. To optimize the intervention, we use control engineers. And one thing that I didn't mention throughout this, but other modules probably hopefully address this, is usability professionals should be involved in every step of design, of experiments, and interventions. And I think that concludes my presentation, and thank you for your attention.